All right. Okay, so we're looking at number 7 on 8.6. It says consider the function natural log 1 plus 15x. Write a partial sum for the power series which represents this function consisting of the first five non-zero terms, blah, blah, blah. All right, so and the number 10 is very similar. It's the arctan of x over 15. And I think it's just by happenstance that they have 15s in there. All right, so I'm going to stop the share and I'm going to go to my overhead here. How do I do that? I always forget. Here we go. Let me get that enlarged. Okay, well, we're going to do a little trick here. Both the natural log and the arctangent have a special kind of derivative. I'll do with the log one first. So y prime, it's 1 over 1 plus 15x times 15 because of the chain rule. Okay. Now, this particular form, you should remember this. This is kind of like your basic form you should know. The 1 over 1 minus x. Oops, squared too early. All right. So this is a basic form that you should know. What we're going to do is we're going to adapt this form to look like this. We'll write out a few terms, and then we will antiderive it to get back to that guy. So the way I'm going to do that, the numerator 15 is just a spectator. We'll put that on last. It's the 1 plus 15x. I want to turn this 1 minus x. So replace the x with minus 15x. And what happens is the minus and the minus make a plus, which is what we want. But check this out. What happens is all these x's here get replaced with negative 15x. So it becomes 1 plus negative 15x plus negative 15x quantity squared plus negative 15x quantity cubed. I'll do it one more. Plus negative 15x quantity fourth. Oops. Oops, sorry about that. So, and then I'll simplify that just a tad. So you'll notice we get an alternating sequence, or actually a series in this case. Now the square squares away the negative, it's 225 x squared, and then this negative stays 15 cubed. I forget what that is. 3375. Let's do one more. 15 to the 4. 50,625. Now I'll pause here. So far, so good. Does everybody see what I'm doing? Taking kind of this
Yeah,
standard model here.
yeah, I understood that part. I
Okay.
think it might, based on that, it seems that in the future when I get questions like this, it might make more sense to write out the sequence and then and anti-differentiate that. Like even if I under even if I know what the full the actual series for the logarithmic function is.
Right. I always do it by hand. After all these years, I have to write everything out. And I always suggest to write out at least five terms so you start seeing the pattern.
Hmm.
Now, one last thing, we're not done. This is actually the pattern for 1 over 1 plus 15x. I want the 15 there. So I'm going to just, so all I'm going to do is multiply by 15. So that just simply tacks on an extra factor of 15 to all of the terms here. So this becomes 15. This becomes negative 225x. This becomes plus 3375x squared. This becomes negative 50,625x to the fourth. I guess we need another one, so it'll be 15 to the 5, which is, oh, geez, 759, 375, x to the 5, dot, dot, dot. Okay. Now, that's the uh, power series for this function here, this crazy looking thing. What I want to do now is I want to anti-differentiate to get me back up to the original. So I'll just lightly put little squiggles there. On the left side, we're back to the original, ln 1 plus 15x. And on the right side, everything was just normal integration. I'll write out a few terms. Actually, you know what I messed up here? That should be a 3. That should be a 4. So the powers didn't change, only the coefficients in this line changed. My bad. So this becomes a 4, x to the 4. This will be raised now to a 5. So 759,375 all over 5, x to the 5, dot, dot, dot. And I think that's what they wanted. Let me recheck the problem. Um, yeah, it actually wants you to type all this stuff in. One, two, yeah, 5 terms. Um, and then the radius of convergence, well, you come back to the um, you come back to this format here. Actually, if I go back up to here, the radius of convergence here is for x between the absolute value of x between 1, which is the same thing as saying this. X is between negative 1 and 1. So what I do is I come down here, and actually, so again, the numerator 15 is just really a spectator. It's this guy right here. And so what I would do is I would say the absolute value of 15x has to be less than 1, which is the same thing as saying x negative 1 is less than 15x is less than 1. And then I divide out by 15. So this actually has a very narrow radius of convergence.
Oh, okay, so I got that part right.
And you know what? I just mentioned it. It's the same. So I actually did it for this guy, this function here, but when you anti-differentiate or differentiate, it's going to be the same interval up to the possibility that some endpoints might be included. But that doesn't change the radius any. All right. I think that takes care of that question. Anybody else? Let's keep this alive here for a moment. Anybody have any question on how I kind of handled this whole thing from start to finish? Feel free to jump in if you do. Well, again, I recommend memorize this guy. This is what this is. This is a geometric series. And this is the short form formula for sum of a geometric series. The first term is 1, and the common ratio is x. It's always the first term over 1 minus the common ratio. And this guy is kind of like a stem cell. You can adjust it however you need to. So if you get a form that has this look to it, you can do this little maneuver. I'll come over here. I'll just, for the arctan, I'll take the derivative. It's going to be y prime equals 1 over 1 plus quantity x over 15 squared, and then times 1 over 15 because of the chain rule. And I know that looks a little ugly. Actually, I'm just going to leave it like that. Um, the 1 over 15 just becomes like this 15. It just becomes a spectator. Okay. What you would do is you would take this form here, despite its appearance, it's good to go. And what you would do is where you do this step, you would replace x, you would replace it with negative quantity x over 15 squared, and then just jot out a few terms. work this guy in at the end, integrate, you'll get right back to the original, and then I guess just do that. So it's really kind of the same question. If anybody wants to take an image of this, I'll tell you what, I'll leave this here for a couple seconds and I'll scroll down. So go ahead and take a screen capture if you want. 3, 2, 1. Then I'm going to scroll and go ahead and take a screen capture of that if you want. All right. And one thing I might recommend if you have the time is you can actually check by graphing. If you're in Desmos, set f of x equal to the original function, which was ln 1 plus 15x. Set g of x equal to the series. Now, it takes a long time to type in, but actually, even after you only type in like a couple of terms, you'll see, I'll say you should see, and I'll put it in quotes, conformation, in that the two functions are actually equal, but you're only going to see that happening in between this tiny little interval. So you have to really zoom in. What series do is it allows us to actually turn other functions into basically long polynomials. Polynomials are just basically addition, subtraction, multiplication, division. And if you can take something that's like, well, ln, which is transcendental, and turn it into a polynomial form, you can actually apply the rules of polynomials to it. It's a good way to do some estimations as well. All right. Any last questions on this one? I, Sam, I think this was yours. Were you good with this?
Yeah, that makes a lot of sense.
Okay. So I'm going to share the screen. 8.5, number 6. Let me copy those down. It's series, the sum from 1 to infinity, 20 to the n times x to the n all over n factorial. And I'm going to copy number 10 down since I've got it up here. It's actually quite similar, except the n factorial is on top. And by the way, whenever you start getting a mix of exponentials and factorials, always use the ratio test. Ratio test is really best designed for these types. All right. I forget. I shut it off too early. Hold on. So the question is, find the radius of convergence of the power series if needed, enter infinity or negative infinity. All right, we'll do this. All right, so I see, Luis, I see your question there. I'll get to it. All right, so let's look at number 6 here. So what we're going to do is we're going to take the limb as n goes to infinity of the ratio of two successive terms, absolute value of the general nth term here. It's going to look really messy for a moment. So you'll notice I'm just popping n plus ones where there had been previously been n's. Now I'm going to flip over the bottom. So the 20 n plus 1 and the x to the n plus 1 stay on top. This n factorial moves to the top. The 20 over n, the x over n now go to the bottom, and this n plus 1 factorial goes to the bottom. Okay. As far as the 20s are concerned, we have n of them on the bottom and one more of them on the top. That means that when they cancel, it leaves us with just a single 20. Same for the x's, it just leaves us with a single x. I should have absolute values, I forgot. And then here's that n factorial over n plus 1 factorial. We're just going to use that little thing right there. It's x over n plus 1, uh, just like that. Okay. And that's it. So we take the limb as n goes to infinity. And in this case, the bottom outgrows any top. So the limb is going to be 0. Okay. And that's actually good news. This tells us that this series is actually convergent for all x. Okay. So it would be, I guess we could say x is between positive and negative infinity. So I guess in your answer, you would type in the radius would be INF, infinity. And it's a fancy way of just saying convergent for all x. Okay. Does that make sense what we did there?
I am tracking.
Any questions?
I don't
No.
think it matters, but did we forget a 20 in the numerator?
Oh yeah, I'll just pop it in there. But you know what? Yeah, it doesn't matter because the n is going to outgrow it. In fact, I could have a million right here, and it would still the limb would go to 0 because the action is happening on the n. So no matter what x is, n will eventually get bigger than it and outgrow it. Yeah, sorry about that. The other one, you know what? This one was kind of interesting because it was true for all n. I'm sorry, for all x. This one, well, you could probably guess what's going to happen here. You've got coefficients that are just going to get enormous really fast. By the time you're at like 2, you're at 400 times 2, which is 800. So this thing is probably going to explode on us, but let's do it anyway. So for number 10, same idea. It's good just to get practice. The numerator is going to be 20 to the n plus 1, x to the n plus 1, n plus 1 factorial. The bottom is going to be 20 to the n, x to the n, n factorial, absolute value. Same thing happens with the 20s and the x's. Now here, the n plus 1 survives. And when I take the limbs, I'll write the limb again. I have 20, basically I have 20x times n plus 1. And again, it doesn't matter what x is, it matters what n does. As n gets big, this thing just shoots off to infinity. So this trend, so no matter what, this goes to infinity. This is essentially the exact opposite of what happened here. In this case, the limit was 0, giving us conversion for all x. Now here, this thing is, well, okay, technically, if x is 0, and in fact, we can go to the original series here. What if x is 0? What is this series trending toward? It would just be a bunch of zeros, wouldn't it?
Yeah.
Yeah.
So in that particular instance, if x is 0, it's convergent. So note, if x equals 0, the series converges.
At 0.
Yeah, pretty much.
And then anything else, it just diverges.
Right, diverges. And what you would say here is that it's convergent at a point. Sorry about that. So since it's only convergent at a single point, the radius is 0. So this is like the complete opposite of the first one, pardon me. That was an interesting one. Does that help?
That helps a lot.
Okay. Any questions that I apologize for forgetting the 20, but it fortunately didn't change the answer in this case. Does anybody else have any questions on this particular one? Okay.
Wow.
I'll leave it up here for a couple seconds if you want to take an image of it. All right, 3, 2, 1. And again, if you do need to see it, I could always put it back. So we have a question here. All right, so all right, there's a couple questions going on in the chat. Um, Unfortunately, regarding having a practice test, no, the one we had in 265, it was just formulated differently. I think it would be nice to have it, but they haven't been prepared. And um, I apologize, but no, we don't have those available. Luis had a question, number 9. Can you be more specific? Was that 9 in the same section?
Oh, that was just when you asked for examples.
Oh, but did you want to
Yeah.
take a look?
No, no, it's fine. It's fine.
Are you cool? All right.
Yeah, thank you.
Okay. This is 85, number 5. This is the series 1 to infinity, n to the 6, x plus 1 to the n, 10 to the n. Then we got, what is that? Is that a 20 over 3? I think it is. I'm going to increase the resolution
Yes,
here.
20/3.
Yeah, geez. All right. Oh, it wants the interval of convergence from yay to yay. It wants the interval, the radius as well. Let's get our hands dirty and do this one. All right. So because this has got a mix of polynomial, this is actually also a polynomial. In fact, we're going to reduce that right now. And then we also got exponential. So what do we really got going on here? 6 would be 18 over 3. And I have 20 over 3. So if I subtract, I have 2/3, and that would be in the bottom. Everybody catch that? That takes care of the ends. For the n plus x, I'm sorry, x plus 1 to the n over 10 to the n, let's just keep those the way they are. And because it's got a mix, and I think I'm just going to go with the ratio test again. It always seems to work nice. Now, if the ratio test fails, I can always try another test. Oops, it's n to infinity. And remember, it's a sub n plus 1 over a sub n. So again, it's gonna be messy. Here's what I've tended to do. I draw myself a big long division line. These guys are just going to be increased by 1, the ends are. Divided by this guy, which is the way it is, but it flips over. So actually the 10 over n and the n to the 2/3 pop to the top. And this guy now goes in the bottom. Right. And again, it's messy. I apologize. So let's clean it up. The n tens up top will take care of all but 1 in the bottom, so there will be a 10 in the bottom. Um, the the n plus one, x plus ones in the top will take care of, well, there'll be one left over because all of these guys will cancel out. So this will be gone, leaving one of these. All right, and what I'm going to do here with the n plus 1 to the 2/3, I'm going to combine them. So I actually have x plus 1 over 10 times n over n plus 1 to the quantity 2/3. I'll pause here. Does that make sense what I did with all the reduction and simplification? I haven't taken the limit yet. I'm just doing still the simplifying. And again, you always pop in with a question if you have one. All right. All right. I'm kind of looking at this. As n goes to infinity, this is interesting because this power stays 2/3. It doesn't change. So inside the n over n plus 1, that actually just goes to 1, doesn't it?
Yeah, that's one.
And so 1 to the 2/3 is still 1. So believe it or not, that limit just disappears to 1. And we're left with absolute value of x plus 1 over 10. Now this is a case where it didn't go to 0 or infinity, so we saw something left over. So the ratio test implies convergence as long as this expression is less than 1. Or I can spread it out a little bit and make it a compound inequality like that. And again, anybody cool so far? Anybody have any questions?
Will Desmos accept that as an answer?
Not yet. We're still kind of working it out. But what I'll do next is I'll multiply by, get rid of the fraction, but multiply all sides by 10. So it's going to be -10 less than x plus 1 less than +10. And then I take out 1. And it looks like this is what I get. So that's my interval of convergence. Now the radius of convergence, so the center is just the average of the two values. The center would be -1, and the radius would still be 10, because you have to go 10 each way to get to the endpoints. And I think that's what the question wanted. Let me see. Yeah. All right. We're good. Violet, you were the one that asked this. Does this help you? Let me know. As far as not getting lost in the algebra, yeah, that's the snake in the grass, so to speak. Really, it's just one of those things where practice makes perfect. I wish I had a magic pill or a magical website I could send you to, but it really just boils down to going really slow, deliberate, and being careful. And just like with any skill, the more you do it, the less mistakes you make. You'll never not make a mistake. There's always going to be some issue. You saw me make a mistake about 10 minutes ago. That happens. But I guess just be really slow. I write everything out. I mean, I get a big old sheet of white paper here. I write big, and I go really slow. If I start trying to think it in my head too much, I get myself lost too fast. So that's my recommendation. I'm sorry I don't have like a faster answer. Shannon asks, what convergence test should we be familiar with? I think we skipped the integral test. And also regarding Taylor Maclaurin, I'll get to that one here in a moment. That's a good one. That's a good question regarding convergence tests. Ratio is probably the most common. The root test is nifty, but only if you're dealing strictly with powers of n. Um, I'm trying to remember what the other ones are. I almost always just revert to the ratio because anytime you've got a mix of types of terms or factors, the ratio test is pretty nifty. I don't know. Let me take a look at the homework questions. Let me see if something jogs a memory here. Because really, the ratio test seems to cover a lot of these. Yeah, I think the ratio test is the big one.
And then if it's
Taylor,
not the rate, if the
go-
ratio test doesn't give you, if it's inconclusive, like how should we, like alternating series test and
okay, yeah. I guess it depends on the type of series you have. For a lot of the ones we just got done looking at in 8.5, the ratio test looks like it would be applicable to all of them. But if you've got like the ones we did earlier, in fact, you know what? I'll bring it back up. This one actually is just simply like I don't even know what you call this test. This is the geometric series test, I guess you could say. This is kind of a standard one for this format, for example. Um, for alternating, yeah, if it's alternating, yeah, you want to check to make sure that the individual terms are trending to zero. That's a necessary condition to have convergence for the series. Um, I don't know. It's yeah. I apologize again. I don't have like a good one size fits all answer for that one. To be honest with you, I always revert to the ratio almost all the time.
okay, so start with the ratio test, but if the
Well,
limit equals one, that's when it's inconclusive.
yeah.
So maybe like just depending on what we have, we just have to kind of think about what is the sequence doing.
Well, okay. If a sequence, that's a good question. If the sequence of terms does not tend to zero, and it's not an alternating test, so it's all plus signs, for example, then the series will diverge. Okay. That's a quick way to show divergence of a series. But to be honest with you, that happens pretty rarely. Now, if the sequence of terms does trend to zero and it's not alternating, that actually doesn't tell you anything. It could diverge or it could converge. Now, in an alternating setting, if the sequence of terms trends to zero, then you do have convergence. Now, you might have absolute or you might have conditional. Then you get into that ball of wax. Um, I would say if you see something that looks like what we had, like I'll bring it up. Here's the one from about 15 minutes ago with factorials and powers and polynomials. Definitely ratio test. Okay. The ratio test will always work on these guys because that's what it's kind of designed for. Um, if you get if you let's say you have just polynomials, in that case, hmm, I'm thinking there's a lot of examples that I could take on. The root test might actually do it, but generally those diverge. Where you have polynomial and n. Yeah, and it's not like you have like a little set list where you always should try this one first and this one second. This is where just having done a bunch of them, you start to get a feel for which one's appropriate. Um, you brought up the question regarding Taylor Maclaurin, and yes, that's an excellent question. I want to hit that with you guys. The E, you need to know this one. I'll write it down. Write down the first handful. About a couple more. That's the Maclaurin series. Maclaurin series and Taylor series are the same thing. Maclaurins are centered at 0. Taylors are just centered pretty much wherever you want them to be. You want to know the E one. The cosine one is it alternates, and it's going to be the even. So it's going to be 1, and it's going to be minus x squared over 2 factorial plus x to the 4 over 4 factorial. Take away x to the 6 over 6 factorial plus x to the 8 over 8 factorial. The sign alternates, and it's the odds. It'll be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. Take away x to the 7 over 7 factorial plus x to the 9 over 9 factorial, blah, blah, blah. These are actually all true for all reals, for all x in the reals. Yeah, I think you should memorize these 3 and should come up with some mnemonics. I mean, you should be able to memorize the E one just because it's got a nifty pattern. It's easy to get the cosine and sine ones backwards. I don't know if there's a good song or mnemonic, but I always just remember that cosine of 0 is 1, sine of 0 is 0. So that just kind of helps you figure out what the leading term must be, and the rest just follows. Okay. When you get to if you take differential equations, which I think a lot of you will be, there's actually a way to combine these 3 into a single equation using imaginaries. It's really cool. And also you'll find that these help you work out solutions where, let's say, for example, you need to integrate e to the x squared. Well, normally you can't integrate e to the x squared because it's just not antidifferentiable, but you can integrate its corresponding Maclaurin series. You would replace all the x's with x squareds, and then you just work them out as though they were big polynomials. You end up getting a series that approximates e to the x squared as its antiderivative, but you take out a number of terms and it's actually quite accurate. So definitely know these 3. You had power rule. Yeah, I think you should just general power rule. What is it? No, I'm sorry, it's C naught plus C1x plus C2x squared plus C3x cubed plus C4x to the 4. And that's not unlike the geometric series we saw with 1 over 1 minus x. And then the arctan, well, the way I would do it is I would take the derivative, which is 1 over 1 plus x squared, and then I take that, again, might as well do it. You asked, so I'll do it. All right, so that's the common form for just 1 over 1 minus x. So what I want is this guy, so I'll replace with negative x squareds. I get an alternating series. Ding. And then when I integrate, I get back to arctan, and I get x minus 1/3 x cubed plus 1/5 x to the 5. Take away 1/7 x to the 7 plus 1/9 x to the 9, dot, dot, dot. And that's actually a pretty cool series. That's a good one too. Yeah, you should know those ones. Definitely the first 3. All right. How you guys doing? You hang in there?
Yes.
We got about time for one more. It's 6:48 Arizona time. And anybody want to ask me one? Okay, so let's take a look at number. Is that the one you were asking about, number 1?
Yes.
All right. So all of these depend on the 1 over 1 minus x form, which I shall copy again. You definitely want to know it. Get it, write it down 10 times or something. Okay, so we want to do the power series representation for 3 over 4 minus x. And all right, so that's the first one. And all the rest of them look kind of similar. And by the way, the numerators, those just wait until the end and then you just distribute them in. It's all the actions happening in the bottom here. All the, oops, don't do that, but yeah, in the denominator. All right. So I need to make this look like this. I need a one where the 4 is. And so what I'm going to do is I'm going to factor out a 4. In fact, what I'm going to do is I'm going to factor out a 3/4. Check this out. Now it looks like that. You see what I did there? The
Yeah.
idea is to make this look like this. And the 3/4 will just become a spectator. That's just going to live outside until the very end, and then we'll distribute it in at the very end. So what I've got is I can now use this kind of format on this guy. We'll do it right now. So we're going to replace all of the x's. And by the way, when it's negative, you don't need to be fancy. Just replace x with x over 4 because it's already the sign's already taken care of. So I have 1 plus x over 4. It's going to be x over 4 squared, so x squared over 16, and then x over 4 cubed, so x cubed, 4 cubed is 64, x to the 4 over 4, so 4 to the 4th, I think is 256. Let's do one more. X to the 4 over 5, I think that's 1024. You know what? I want to make sure of that.
Yeah, it's 1024.
It's 1024, yeah. All right. That's good enough. That gives us a bunch of terms we can play with. And then I can move the 3/4 in just by simple distribution. And all the 4s on the bottom just increase by a power or a factor. So, oops, no, I'm sorry. 3 over 64 x squared, 3 over 256 x to the cube. Let's do a couple more. 3 over 1024. Oops. X to the 4. I'll do one more. 3 over 4096. X to the 5. Ding, ding, ding. Okay. As far as its convergence, all the action is right here. The 3/4 has no effect on convergence. It's all happening right here. We take the absolute value of x over 4, less than 1. We spread that out. Multiply 3 by 4 to get rid of the fractions. And the interval of convergence is -4 to 4. The center is 0. And the radius is 4. Okay. JD, does that help you?
Yeah, I definitely get to that part. The only thing that had me confused was on the answer portion for that question, it just gives me the power series of 3x to the n power over 4 raised to the n plus 1.
Oh, yeah, that's okay. That's what's happening here is that they're, yes,
But I see it happening. It was
it's the
just I was
same
having a
thing.
hard time trying to put that into like words.
Yes. Okay, so you're being asked to then basically summarize this into a single formula.
Yes.
Yes. All right, I'll tell you what, I'll show you. I Is that what the question insists that you do, or I mean, because I think
Yeah,
leaving it
that's what
spread
the
out is,
answers have as far as the answers keys.
I'll tell you what, I'll show you how I used to do it. I'll write out a few more. I want to get a pattern going. What I would do on the bottom is I would actually put the little n values, and they got to correspond to the powers. So just to remind myself which powers I'm playing with. Okay. Because this is really just 3/4 times x to the 0, right? Notice that the 3 is actually not changing. The 3 is staying 3 all the way through. So it becomes 3. The x's just are to the power of n, so they seem to agree. But the 4s are actually a power, because normally 4 to the 0 is 1, and 4 to the 1 is 4, and 4 to the, you see I'm off a little bit. It's
Yeah.
actually going to be 4 to the next higher power. And I have to adjust it slightly. And that way, if I go from 0 to infinity, that should be my general form. That's how I do it. I just
That's
kind of
the
piece it
answer.
together. All right. Well, guys, it's almost 7 where I'm at, and I'm going to go ahead and power down here. This will be on, I'll send out a link probably in an hour or two. If you're in Professor Maris's class, I'll give her the link and then she'll send it out via her announcements. And then this will be available if you want to catch up later. I appreciate you guys showing up. I know it's a couple days early. I wish you all the best. Um, I'll see you probably next Monday because I think I'll do this again for the final.